Please make me the co-host.
Yes, and now you are the host.
I hope the screen is visible.
Yes, sir.
Yes, sir.
We were on this part of our discussion, and we now need to move forward to some of the important items related to virtualization. And I hope you all are aware about the role of virtualization in the cloud computing from this diagram. If you see, we have multiple physical servers. We are aware about them. They are running virtual machines. We are even aware about them. These virtual machines may be standalone virtual machines, or they may be containerized. They may run containers inside them, right? Now, the important part is these two building blocks, which you are seeing at the below of the diagram, they are already available with us. Now, what cloud is bringing then? See, cloud is bringing the business logic. If you see, there are service request examiner and admission control modules, which are taking the requests. Finally, pricing and accounting is there, which will allow you to prepare the bill, ask for auto scaling, increasing and decreasing the resources, and migration. Right? So if somebody asks me, sir, we know hardware, we know virtualization, we know containerization, then what is cloud? Is cloud virtualization? So the answer is yes, cloud has virtualization as part of it, but there is more important items like business logic, migration, auto scaling, and VM placement. Right? These are the four important things which are needed for a data center to become a cloud. You know these primary things like types of clouds. I don't need to discuss them, right? We know about public, private, and hybrid clouds. Yes. Anybody can confirm? Or do I need to discuss a bit about them? See, the answer should be the binary answer, right? So you can write on the chat if you know about it, and we can discuss a bit on them. Okay, you are aware. Okay. So now I'm moving forward, and we are taking a leap towards some of the important papers. And let me discuss the first paper in this direction, which is this one. I already told you about this paper. This paper is already available in the repo which I shared, right? And the paper's title is Gen and the Art of Virtualization. Now let me take a bit of time on why this paper is important and why we should study from research papers at times. See, the first motivation for me to show this paper is we need to start respecting the academic institutions, right? This paper is an outcome of Computer Laboratory Cambridge, one of the most important lab in this world in the systems side. Most of the important products, when you go and buy in the market on the system side, they are originated from the academia. That is one point I would like to make. So if you read the names Stephen Hentz, Tim Harris, Ian Pratt, right, Andrew Warfield, these are the top professors at Cambridge who made a lot of breakthrough contributions in the area of system side, operating systems, kernel, system security, distributed systems. And Gen, which has changed the world of virtualization, is a product of university laboratory, right? So most of the times when Professor Chaudhary would also agree with me that, companies come for the placement and say that your graduates are not employable, this and that, blah, 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 right? I would like to make a point here that universities are not here to teach new languages, tools, framework. Universities are there to teach fundamentals, right? So that tools can be built, products can be built. They are not here for your IT services. They are product builders. And we need to see India seriously for product builder economy, right? We are mostly IT services economy, right? And that is why our IT is considered as inferior as compared to the IT of Europeans and US, right? And this one point you would understand only when you would think about the products which India created in its software industry. We have created minimal products. We don't create products, we test them. We just test them and say they are okay or not, right? So if we want to really become an economy which whatever people are talking about multi-trillion economy, it's only the products which will make the economy, right? So this product, which has a larger share today in the virtualization industry, is created by the industry, by the students like you. There are undergraduate, masters and PhD students which created the GEN, right? So this is one of the important points. Let me reiterate. GEN is an hypervisor, a virtual machine monitor, but most importantly, GEN is an operating system. It is an operating system which can manage virtual machines. Most of the operating systems out there manage processes. This operating system manages virtual machines, right? So if you look at the venue of this one is SOSP 2003. SOSP, if there are master's students, I would like to iterate that SOSP is top notch. SOSP, OSDI, and NSDI. These three are even ahead of IEEE transactions. Having one paper there is very, very difficult, right? Only the landmark contributions get published there from the product space. They should be complete products. Okay. What kind of virtualization GEN offer? We discussed about types of virtualization. Can anybody recall what kind of virtualization GEN offers? Is it para virtualization or full virtualization? I think we took a long gap of 15 days. See, GEN offers both kinds of virtualization. Even the third kind of virtualization is offered today, but it is most importantly known for para virtualization. They created GEN mostly for para virtualization so that on the commodity hardware, we can work with greater performance. So most of the instructions are directly executed. Some of the instructions which do not follow the properties of Goldberg and Popek, they are ignored. I hope you can recall this discussion, right? Okay, so let me quickly go through what this paper says, and I'll tell you how to read the papers. I earlier also described how to read the papers. And you know, at times some people may feel that the language of the papers is too critical. We cannot comprehend from it. But please accept one thing from my side, that at first instance you may feel that they are difficult, but if you will read them, let us say twice and thrice from the first instance, you will realize that they give more idea about any topic than the books, because they are written by who created the product, right? So the first idea about GEN can be taken from the abstract. And let me talk about what they are saying. I'll read it because I want you to read it with me. I hope this is visible. Numerous systems have been designed which use virtualization to subdivide the ample resources of a modern computer. Some require specialized hardware or cannot support commodity operating systems. Right? This line is important. Some require specialized hardware. Full virtualization wanted specialized hardware that we get in, you know, Intel, AMD, and AMD IVT. But this tool, they are saying that some target 100% binary compatibility at the expense of performance. Others sacrifice security or functionality for speed. So this is how you start. You talk about whatever current tools available and what problems they have. What is 100% binary compatibility? Emulation, right? You are writing the whole set of instructions in the emulated software. Few offer resource isolation or performance guarantees. Most provide only best effort provisioning, risking denial of service. This is a very important attack, denial of service. You might have heard about DDoS, distributed denial of service. So when you talk about resource isolation, we want that every virtual machine or every container should get their share of resources without getting affected by other co-tenants, right? Okay, so what is this paper about? This paper presents Gen, an x86 virtual machine monitor, which allows multiple commodity operating systems to share conventional hardware in a safe and resource managed fashion, but without sacrificing either performance or functionality. Okay, what is their aim? Our design is targeted at hosting up to 100 virtual machines instances simultaneously on a modern server. Single server, 100 virtual machines. I should tell you that it was published in 2003. Today it is 2022. 2022 we are living. Today, Gen can run 480 virtual machines on a single physical server. This is the amount of work they have done. In a cloud server, on a single physical server, we can run 480 virtual machines on a single go. So you see kind of scheduling we require, kind of resource allocation, VM placement, and all the other algorithms we require, right? What is the beauty of Gen? The virtualization approach taken by Gen is extremely efficient. We allow operating systems such as Linux and Windows XP to be hosted simultaneously for a negligible performance overhead. Why there is negligible performance overhead? Because we are ignoring instructions which do not follow the Goldberg and POPX requirements. At most a few percent compared with the unvirtualized case, right? So this much is sufficient for us from this abstract. Let me go into the presentation mode. Is this visible to you? Yes, Kirtan? Okay.
Yes, sir.
For your help, I have given a paper which is highlighted. Only that highlighted part, if you read, you will be able to know what requires for a systems product to be developed, right? And it is like rewriting a complete operating system. So full virtualization, we know what are the disadvantages. You are emulating certain instructions, and emulation happens in software, and software is always slower than the hardware. I hope we all agree with this. We discussed this in detail, right? Software implementation is always slow, much slower than the hardware implementation. Now, some of you, I think there are few names which I did not see in the last lecture. You may realize that software will also run on the hardware. Ultimately, if you implement something in the software, where will it run? It will run on the hardware. So don't get confused. It will run on the hardware, but the software implementation will always be longer than the hardware implementation in code, and that is why it will be slower, right? Now, but when you read the classical papers, you get a feeling that what they are doing and how clearly they write. See, most of the students, when I train them, I always say that technical aspect is one side, second aspect is articulation, and third aspect is text writing. How precisely you write what you are doing, right? So please see what they do. We distill the discussion so far into a set of design principles. What are the design principles? The first one is support for unmodified application binaries is essential, or users will not transition to Gen. See, when they created the product, they said, you don't need to change any application. Because if you ask them to change the applications, user will not come to the Gen, right? So first thing is unmodified applications, okay? Second one is supporting full multi-application operating system is important. Multi-application operating systems. What do we mean by this? I talked about LAMP server, Linux, Apache, MySQL, PHP. It is a multi-application server, right? This support is required. Third one is para-virtualization is necessary. It gives you high performance. Why high performance? Almost all the instructions execute directly on the hardware and ignoring the other instructions. And it provides strong resource isolation on uncooperative machine architectures. Why uncooperative? Because they don't follow Goldberg and POPX requirements, right? Even on cooperative machine architectures, completely hiding the effects of resource virtualization from guest operating systems risks both correctness and performance. Correctness is important the execution order of the instructions. Because there are certain instructions which are sensitive but not privileged, correctness may not be ascertained. But in para-virtualization, we would like to have it. Okay. So this was one piece. Let me go to the second portion. I would like to also suggest you that we have discussed each one of these at greater length when we were discussing each individual resource, like CPU virtualization, how should it happen? Memory virtualization, how should it happen? Disk and network in general, without talking about any specific, hypervisor. This table is very important. It tells us x86 interface of the hardware, how virtualization will happen in Gen. Right. So let us talk about memory. We follow paging and segmentation. We all studied paging and segmentation at greater length in operating systems. So we know pages are equal sized, segmentations or segments are of unequal size, right? But the segment tables are smaller, page tables are larger. So what do we do? When we are following segmentation, we cannot install fully privileged segment descriptors and cannot overlap with the top end of the linear address space. What do we mean by this? See, there are multiple virtual machines, single hypervisor. Every virtual machine has their own dedicated RAM from the bigger RAM we have on the physical machine. So when we talk about a bigger RAM, which is handled by the host operating system, all the VMs will share that RAM and cannot overlap the RAM of other VMs, right? So segment descriptors are very important. But these segment descriptors cannot be fully privileged. Why? Because you have a segment table with the host operating system, and then you are talking about segment tables at each individual VM. We require one additional mapping from one segment table to the other segment table, right? And this makes the things difficult. Those of you who are here in earlier sessions, you would realize that everything we discussed, whether files, memory, CPU, one additional layer was coming up. Yes, CPU, one additional layer of scheduling. Files, one additional layer of conversion. Memory, one additional layer of address translation, logical to logical, again logical to physical. Those additional layers are required. Similarly, when you do paging, every virtual machine is running an operating system. They will do their own paging, and you will have paging at host operating system. You require one additional conversion. Yes. So guest operating system has direct read access to hardware page tables, but updates are batched. Reading is okay. Writing is not okay. Is reading okay? If I allow a guest operating system to directly reach pages from the RAM of host operating system, is it okay? Yes, it is fine. Reading doesn't change anything. Writing makes things difficult. So what do we do? Writings or updates are to be batched. Who will validate them? Hypervisor. Yes. CPU. We discussed about a ring architecture, ring 0, 1, 2, 3. And I highlighted this point that ring 0 is the most privileged. And it should be governed by virtual machine monitor. But then all the guest operating systems are disappointed. They wanted to run at ring 0. Why? Because they want to be highly privileged. Yes. So what is the solution? Intel said we will create a ring 0 dash. Ring 0 dash, right? And any VM which wants to run in fully privileged mode can run in ring 0 dash, not in ring 0, right? And then they can go forward. But this paper is of 2003. Remember, there was no ring 0 dash. So what they decided? They said guest operating system must run at a lower privileged level than Gen. So ring 1, 2, 3. Guest, what about the exceptions? Exceptions will be taken care by bit vectors. We discussed about interrupts, right? Virtual bit vectors for every virtual machine will get the interrupts and then will deliver it to the virtual machines. What will happen to the system calls? System calls require a context switch. We all remember this. User mode to kernel mode, coming from kernel mode back to user mode, right? What will happen to the system calls? See, so we require an additional thing, a fast handler. In Gen, we have hyper calls. These are the fast handler, so that every application can directly call to the guest operating system without involving gen. Right? This support we require. Interrupts. I'll talk about a very important data structure here for interrupts. Many times students ask, sir, what is the purpose of data structures course? A very interesting data structure was created by Gen to deliver events to virtual machines. Because I hope you can recall that all the IO will be managed by Gen on behalf of virtual machines. So how those events will be delivered? I have a single mouse, I have a single speaker, I have a single set of IO devices. So there requires somebody who can manage these things. So we give this opportunity or this responsibility to virtual machine monitor. But now how virtual machine monitor will see or give mouse, speaker, keyboard to every individual virtual machine? That will happen through that important data structure. Time. We have a single clock on our machine. How time will be decided for every virtual machine? See, this is a very important problem. A virtual machine is scheduled right now. It ran for 2 seconds and then it was interrupted or preempted. For next 10 seconds, it is not getting CPU. How will it, calculate its time? Because I have a single clock which is governed by host operating system, right? So what we need to do? We need to maintain multiple clocks, real clock, system clock, and virtual clock. And then we need to again and again calculate whenever a VM is coming to CPU, it should first look at its time, whether my time is updated or not, right? The last point is device IO, device input output. I gave a brief. Then data structure which handles interrupts will also handle this. So let us go ahead. Those of you who are really interested in knowing the system side of operating systems should read this paper at full length. Right? It is not a very difficult paper. They wrote it, I think they wrote it for undergraduates, let me tell you, so that everybody can grab from system side. Okay. This table will motivate all of you. When they modified the operating systems so that they can run Gen, how many lines of code they changed in operating systems is given in this table. Linux, there are 78 lines of code which are architecture independent. Network drivers 484 lines, 1000 lines for virtual block device driver. What is virtual block device driver? Hard disk. Block device is hard disk. Character devices, mouse and keyboard are character devices, but hard disk is a block device. These are Gen specific code, around 1300 lines. So total, how many lines they wrote in an operating system? Around 3000 lines. Only 3000 lines were written to change an operating system from a commodity operating system to a virtualized operating system. How about Windows XP? Around 4620 lines. They are doing it for everybody. No user has to modify the code. They will do it automatically. You just, while installing, they will change the code, right? Coming to the next point, this diagram, let us see. What is domain 0? Domain 0 is host operating system. Domain U is virtual machines. Here one point is coming up which is known as Geno Linux. Geno Linux. It means genified host operating system. So how do you install Gen? Gen can be installed in 2 ways. First way is bare metal. Directly install on the hardware. Second method is you first install the operating system of your choice, like Ubuntu, Kali, whichever you want, CentOS, OpenSUSE, Red Hat. Then you install Gen to modify the kernel of the host operating system. It can be done within few minutes. So what will happen once you install a Gen on top of the host operating system? Nothing will happen. Your host operating system will remain same. Only the kernel will be edited and some augmentation will happen. Some additional modules will be given to the kernel. So I call it genified kernel, and that kernel is known as Geno Linux, right? So all will follow this, and you have domain zero control interface, which is genified kernel, right? Your user softwares are running in all the guest operating systems. You may want to run control plane software or hypervisor in one of the kernel. So remember, somebody may ask this question: is host operating system running on a virtual machine? The answer is yes. Host operating system is also running on a virtual machine. There is no difference between a host operating system and a guest operating system. Okay. Now, what is the purpose of specific system calls we create in Gen? An important addition to Gen is hypercalls. What is a hypercall? Two mechanisms exist for control interactions between Gen and an overlaying domain. Who is domain? Virtual machine and an operating system running on top of it. It can talk to Gen. How it can talk to Gen? Using hypercalls. Using hypercalls. In a normal operating system, how a process can talk to kernel? Using system call. Similarly, a guest operating system can talk to a hypervisor using hypercall. Right? These hypercalls, you don't need to do anything. While you install an operating system, it will be modified so that it becomes capable of running hypercalls. Right? So let us move ahead with one data structure, and I'll explain this data structure at little greater length. Can you see this diagram? A circular ring which is visible. See, what is the purpose of this data structure? There is a hypervisor. There are multiple virtual machines which are running guest operating systems. How input-output events will be delivered from hypervisor to guest operating systems, and how guest operating systems will request for input-output from hypervisor. We require a common mechanism so that they can talk to each other. That common mechanism is known as input-output rings. You can see this diagram. This is known as asynchronous input-output rings. What is the purpose? Data transfer between Gen and guest operating system. Its nature is circular. We created circular linked lists in data structures. The purpose is quite similar. How many pointers are there? There are 4 pointers. What is the purpose of each pointer? Let us see one by one. Let us talk about the pointer here. Response producer, shared pointer between Gen and guest operating systems, but who can update it? Updated by Gen. Okay. Request consumer, this is a private pointer in Gen. Who manages this? Gen manages this. Request producer, shared pointer, but who updates it? Guest operating system. Response consumer, private pointer in guest operating systems. Let me simplify this. There are 2 pointers which are shared between guest and Gen. But each of these pointers can be managed by either Gen or guest operating system. Right? These pointers are shared in nature. So there are 2 entities which can see them, but only one of them can update it. Yes. Then there are 2 pointers which are privately held by either Gen or guest operating systems. So you can recall a problem, producer-consumer problem from the operating systems used in critical section, right? And producer-consumer problem can provide pure mutual exclusion or a solution to the critical section problem because it follows all the 4 properties of bounded weight, mutual exclusion, no preemption, and progress, right? The same producer-consumer problem is used here. What happens? Consumer says, I have these IO requests. it aids them to this IO ring. Gen completes those IO requests and updates those pointers. So guest will be able to know kitna kaam ho gaya, kitna baki hai. Yes. Similarly, Gen receives some input from IO devices for certain guest operating systems. It can aid them using shared pointer, and a guest operating system can read these data structures to know what IO request has come to it. Single data structure can become a complete mechanism for all the guest operating systems and Gen to talk, right? We require this kind of a design. Can they affect each other? No, they cannot affect each other because pointers are either shared or private. Private pointers can only be checked by them or changed by them. Yes. So this single data structure is very important for the input output, and it can be very well managed, right? Okay, now the last concern about how time is managed by Gen, because remember, time is a very important entity, and if you can recall, while we were studying Goldberg and Popek, there was a term called recursive virtualization. Recursive virtualization. क्या मुझे कोई बता सकता है recursive virtualization क्या है?
So sir, there would be a virtual machine. Inside that we will create multiple virtual machine. Inside that there might be multiple virtual machines. Very good,
Sameep. This is the real definition, but what are the requirements? How do you ensure that recursive virtualization is happening? Let me give you some hint. All the properties of Goldberg and Popek should be fulfilled for recursive virtualization. Yes?
Yes.
Okay. What was the second thing which was required in recursive virtualization? See, recursive virtualization wanted virtual time should be maintained well. If time can be managed, recursive virtualization is possible, because in recursive virtualization, what you are doing? One hypervisor, multiple virtual machines. On top of a virtual machine, you are running another hypervisor, which is creating multiple virtual machines inside. Now, what is the problem? We already have a problem of maintaining time with multiple virtual machines. Now there are virtual machines inside a virtual machine. So how would they know what is the time right now? One idea is use NTP, Network Time Protocol. Right now the whole internet uses NTP, right? We all use NTP, all web servers, all web browsers. You know most famous NTPs, right? ntp.fedora.org, ntp.msdn.com, right? These are the popular NTP servers, ntp.ubuntu.org. They give time. Whoever asks the time, they give it to you. One idea is that. Second idea is, if you are not connected to internet, how will you get the time? Then you need to ask, whenever you are getting scheduled, first ask what is the time, and then get resynchronized every time, because you are behind, you are running behind. Suppose for next 10 seconds, the VM does not get scheduled and its time becomes older, then before getting scheduled, the time should be confirmed, right? So this is what they have written, that wall clock time, which is the physical time, real time and virtual time has to be maintained. Gen provides guest operating systems with notions of real time, virtual time, and wall clock time at the nanoseconds level, right? So this is one important thing, because if they go behind the time, there will be a lot of issues related to synchronization, right? Okay, for me, this much idea about Gen and its development is sufficient. But there is a second part of the story, that when you are talking about a new product, you are creating a new tool, you said all good things about it, and everybody is impressed. It doesn't go like that. You need to show through experimentation how your tool fare with respect to other competitive tools. And this is known as comparative benchmarking. Comparative benchmarking should happen. So when you are creating a new hypervisor, you cannot just directly say it is good. You need to clearly show with respect to state-of-the-art hypervisors, compare by benchmarks. So what are the benchmarks? Can anybody show light? Benchmark किसे कहते हैं?
So, sir, benchmark is generally like a standard or a reference point from which you can compare other stuff.
Okay, good. Yes, so benchmark are standard set of tools or procedures which we can run in the similar settings on different platforms and compare their performance. So right now I have a laptop, and suppose I want to compare the performance of my laptop with your laptop, Sameep, right? Both the laptops have different configuration, but we want to check which laptop is better. Now this statement is imprecise. Let me make it very precise. Which laptop is better from the perspective of CPU, network, disk, and IO performance, right? So suppose I want to measure the performance of my machine and your machine from the perspective of CPU. How should we measure? So let me help you with this. Let us write a C program, and that C program runs certain instructions, right? Floating point operations, loops, mathematical equations, and the program is created, is available to you and me. The program should also have self-sufficient conditions in which it calculates certain parameters. Kitna samay laga, how many registers were used, what is the total kind of outcome, and a total test completion time. Program runs on my machine, I run it, it gives me a final sheet. This is the performance. The program is run on your machine, it gives the final sheet, what is the score. Based on that score, we can compare two machines. Yes, this is known as benchmarking. Now, benchmarking is not that easy. When I'm running the benchmark on my machine, all these settings should be similar to what your machine has. No additional processors, no network connections, nothing. Experimentation should happen with fair settings. Yes. So this is known as law of experimentation. Law of experimentation. So let me give you one very good name of a person which you would cherish. The person's name is David Patterson. David Patterson is a professor at University of California at Berkeley. We read a paper of Berkeley. Yes, Berkeley View on Cloud Computing. Professor David is also a ACM Turing Award winner in 2018. I hope you know what is ACM Turing Award. It's equivalent to Nobel Prize in Computer Science, right? And Professor Chaudhary may recall, we met David Patterson at HPCA in 2009 or 10 at IISc Bangalore. Yes.
2008, perhaps, right?
2008. Yes.
2008. Yeah, IISc. Yes.
IISc. Yes.
Yeah.
So David gave a law known as law of experimentation. And this law is nothing very new, but somebody big says this, then it makes an impact, right? If I say that this is an experimentation law, nobody will listen to me. But when David says, everybody will give attention. So David says, whenever you are doing some innovation in system side, first do experiments. That yes, this is the real problem. Improve on it. Again, do experiments and show that this really works. Without experimentation in system side, nothing is possible. And those experiments should be reproducible. What do we mean by reproducible? Suppose Kirtan did certain experiments and said that this is a new product which outperforms Gen. I'll say, Kirtan, I agree with you, but give me whole code, give me whole data, give me the configuration of machines. I'll reproduce the same experiment at my campus, and we'll see whether it really works or not. This is known as reproducible research. And this is very important today. Most of the top conferences and magazines and journals in system side are talking about reproducible research today. Even the life of reviewers is becoming very difficult. We need to repeat all the experiments to prove that yes, those experiments sustain, right? So let me go to that part of experimentation which this paper does. Yes, this diagram is visible. So relative score to Linux. Linux, Gen, there are 4 tools which they have taken: Linux, GNU/Linux, VMware Workstation, and UML, User Mod Linux. This is also a very good hypervisor. Now, it is not anymore in the development, but it is there, right? How they are comparing? They're comparing using these benchmarks. The first benchmark is known as SPEC. It is a very popular benchmark, right? So today, if you go and buy a machine in the market, even in the government organization like at Central University, whenever we buy a server these days, we need to specify SPEC rating. Just specifying by RAM processor doesn't work. SPEC rating. SPEC rating clearly identify what is the performance of the machine. So a good server machine will give you a SPEC rating between 130 to 250. So I will run this SPEC benchmark. It is a zip folder having C programs. You directly run them. They will give you the SPEC score, right? So SPEC score. This is INT 2000, an old benchmark. Linux build time. Most of you install Linux operating system directly through the bootable, pen drives or live CDs. How about building the Linux from source code? Has anybody tried? Downloading the source code of the Linux kernel, then installing it, right? Believe me, we should always do this activity as part of system side. Building a kernel from source code. You do it, it will take hours, but you will realize so many good things. See, Ubuntu has made life very simpler because Ubuntu is striving to become Windows. They want that everybody should use Ubuntu. However, building from source code is an important activity. So Linux build time, OSDB, this is a database benchmark. OLTP, this is also a database benchmark for transactions. Dbench is a free database benchmark, and Web99, this is a web server benchmark, again from SPEC. So SPEC is not free. You need to buy the licenses. Otherwise, others are free. You see, according to them, Gen is having a very good score, and it is comparable to a normal Linux, a native Linux. 567, 567, 263, 271, 172, 158. This is how they are comparing and saying that we are around similar, and the market leaders like VMware are showing very poor score. This also they said, right? Because it is SOSP, this has to be reproducible research, and they are faring well as compared to these tools, right? Now, many of you are doing course projects, and benchmarking is a very good activity which can be done for comparing such things, right? So it is 4:57. We have at least around 20 minutes in our hand. So whatever Jen said, we may also agree that whatever Jen will say about themselves, it will be all good, right? So we require a third-party benchmarking as well. So there is another paper we should see, which is visible on your screen, a component-based performance comparison of 4 hypervisors, right? And this is a good paper. Why good? Because any student at whatever level it is, they can also run similar benchmarks. They are freely available. Whatever tools they are interested in comparing, they can compare. Because the first step of development is comparison. We should first know what hypervisors are doing, right? And how do we compare them? We all know about IBM TJ Watson Research Center. This is one of the important labs, right? And there are 2 universities which they collaborated, right? George Washington University. I'll directly go to the comparison how they are doing, right? So with whom they have compared? Hyper-V, KVM, vSphere, and Gen. In earlier paper, they compared Linux, GNU/Linux, and KVM and UML. Here they are comparing Hyper-V, which is from Microsoft, KVM, which is open source, vSphere for VMware, and Gen from Citrix, right? So a third party comparison is very good here. Linux compile time. So Gen is taking more time. vSphere, KVM, and Hyper-V. This result is little opposite as compared to the earlier result we have seen, right? See, my idea is not to see what the results are. My idea is to teach you a bit about benchmarking. So let me talk about certain tools which they have used. They're freely available and anybody can use them. This table shows a comparison between these 4 hypervisors when they were released, what kind of architecture they have, what kind of virtualization they support, right? So Hyper-V and KVM and vSphere all are bare metal. On the other hand, Gen is hosted. And they also write controversial in the bracket because Gen also talks about bare metal. Gen server is bare metal, right? Para virtualization, Hyper-V is para and hardware assisted. What is hardware assisted? Hardware itself supports virtualization, right? So after 2007, hardware assisted virtualizations came into the picture. Ren 0- came, and then it supports all the properties of Goldberg and Popak. Gen supports all 3, para, full, and hardware, right? vSphere supports full as well as hardware assisted. So today, almost all the hypervisors in the market, they only mostly run on hardware assisted because hardware is changed now, right? There is a comparison on CPU scheduling, SMP scheduling, memory translation, disk management, and network management. A bit about it. See, most of the scheduling algorithms of these hypervisors, I gave you an idea earlier that there is one additional layer added in scheduling vCPUs to physical CPUs. So every hypervisor does their own job by different kind of scheduling algorithms, credit scheduling, SCDF scheduling, right? Then batch scheduling, different scheduling algorithms are there. Yeah. So let me go from here, benchmark, and this one. The first tool they use is known as Bytemark. Bytemark. This is freely available. What this tool does, Bytemark is primarily designed to stress the capabilities of the CPU. It tests a StarNix Unix, Linux machine in different ways and runs both integer and floating point arithmetic tests. So it continuously runs floating point and numeric tests. What are the 10 types of workload? Numeric sort sorts an array of 32-bit integers. String sort sorts an array of strings of arbitrary length. Bit field executes a variety of bit manipulation functions. Emulated floating point package. Fourier coefficients. I hope we have heard about Fourier transform. Assignment algorithm, Huffman compression, idea encryption, and neural network. And finally, LU decomposition. These 10 algorithms are there in the benchmark. You run them on different hypervisors inside the virtual machines and see what is the performance. This is for CPU. Second one is known as RAM speed. As the name suggests, it is for knowing the cache and memory bandwidth for RAM. So this can be used for RAM speed. Third test is known as Boni++ and file bench. What is Boni++? Boni++ measures disk throughput for a hard disk, right? So how would you make a disk benchmark? Write single byte, read single byte, delete single byte, erase single byte, See, deletion and erasure are different, right? Then random read, random write, random erase, random deletion. This is for single byte, 2 bytes, 4 bytes, 8 bytes, 1K, 2K, 4K. You continuously do this. That is how we compare disks, right? Then comes up the file bench, which is file system benchmarking, because every hypervisor has a different file system. So we need to also compare that. Finally comes the network performance. How do you perform, compare networking of different hypervisors, create connections, send data transfer, UDP and TCP data, and then compare. Finally comes the application workloads. What can be application workloads? Web servers, database servers, right? These are application workloads. So there is a very good tool you can read here. We test a larger set of applications using the pre-bench software. This is freely available, pre-bench software. You may want to use it and compare. This suite has multiple software. What are the softwares? Let me try to read it from this table, this figure. bzip2, which is compression. OpenSSL, this is an authentication benchmark. Then ProWay, this is a gaming. DCRO, again a gaming thing. ID, SC Mark II, bzip2, OGG, and GNU Go. These are the kind of applications they run in FreeJet, right? They also test multi-tenant interference. Multiple VMs running together, do they affect each other? And then they compare. I don't want to go to the results that which does better, because this is an old study. These tools have changed, right? But this is how the comparison happens. And whenever you do comparison, those comparison have to be repeated for multiple times. They have to be re-informed, confirmed, and you need to also talk to the companies which are providing these tools that we have done this. You may want to do reproducible research so that we can compare, right? Today we have a large number of hypervisors, right? Even hypervisors for containerized platforms there are many, right, which are providing better isolation and better virtualization. Now, when we could do first thing about Gen and then the comparison of hypervisor, let me talk about an additional aspect of virtualization which made the things of data center management quite easier. So let me share the board and discuss one important problem which is very interesting and can provide us a lot of opportunity of optimization, which is known as VM migration, virtual machine migration. This diagram, which I am creating here, depicts two physical servers in a data center. This is physical server 1 and another physical server which I have is physical server 2. This physical server is virtualized. It means it has a hypervisor. This also has a hypervisor. I write VMM for short. There are multiple virtual machines they are running. 2 virtual machines and it is running one VM. The name of the virtual machine is VM1, VM2, and then VM3. Okay. See, there are certain conditions in which we may want to move this VM1 from this place to this place to this place. And we call this movement as migration. See, one easy idea is we do stop and resume. What is stop and resume? I switch off this VM1 on physical server 1, shut down, copy the disk of virtual machine 1 from here and paste the disk of virtual machine VM1 over here, and then restart here. This is a good mechanism, works well, but it will take some time. How much time? Suppose the disk size of VM1 is, let us say, 20 GB. It would require to copy this 20 GB in a disk, in a pen drive, or in a shared folder over the network, and then paste it over here and then restart. It may require around 10 minutes to do the whole job because it is a manual activity, right? But it will work fine. But in the cloud, when you want to do this, who will go and take a copy of the virtual machine 1 and paste it on another physical server? It is not possible, right? So there is something known as live virtual machine migration, which talks about migration without switching off the operating system. So it should work like a magic. Virtual machine VM1 is running, let us say, Ubuntu, running a web server. Web server is serving the requests. And immediately you say migrate. So web server should keep on serving the request and get migrated seamlessly without having any downtime to physical server 2 and keep on serving the web server requests. If this happens, it will be a magic for all the web server owners, because what is happening? No downtime, and you are getting migrated from one physical server to another physical server. It is quite possible in live virtual machine migration with a downtime or migration time. See, they are two different things, but which I'll explain, around less than 1 second. Less than 1 second. How would it happen? Without, because nobody will feel a 1 second downtime. 1 second is nothing. And you will have a much bigger server with a lot of resources available for your virtual machine. See, why we are doing migration? We are feeling scarcity of resources, or our related VM is placed on physical server 2, or physical server 1, the cloud provider wants that there should be more space for VM2, so VM1 should be migrated. All reasons may be there. Now, can you suggest me how can we achieve less than 1 second time when we are taking around 10 to 20 minutes time for a 20 GB disk to paste, to copy and paste on the other physical server? 600 seconds to 1 second. Any idea? Is it possible to transfer 20 GB data in less than 1 second over an NIC card having 1 Gbps connectivity?
No, sir.
Not possible. Anything which you feel can be done? Any idea?
Duplication or pre-scheduling if we know that where we want to migrate, some kind of duplication.
Okay, so you are saying that if we know that you are going to get migrated at physical server 2, we can keep a copy ready there. Is it what you are saying?
Yes, some kind of scheduling would be possible if we know the other server.
Okay, so let us say physical server 1 knows that physical server 2 is the place where we need to migrate. What scheduling do you require?
So, for example, there are some backup algorithms where we iteratively update our backups. So similarly, we can do something. We may be able to do something for the VMs also, that iteratively, or we can do something that if the amount of data has changed is exceeding like this limit, then we will again do a backup.
Okay. This is a fairly good idea. Yes. Anybody else? But would you be able to do this within less than 1 second?
Not if we already had copied some of the things.
So what would you need? How much time would you need?
So if we were just talking about the limit, then we would need so the limit was 1 GB, right?
1 Gbps.
Yeah, so
And,
we would need 20.
remember that this 1 Gbps has small b, not a big B.
Okay.
Yeah, and this small b represents bits, and this big B represents bytes, right?
Yeah.
So on a 1 Gbps channel, even to transfer 1 GB, capital B, you require 8 seconds. Okay, but good. This is a good direction you gave, right? And the solution which I'm going to show you takes a lot of motivation from your idea. Anybody else? 8 into 160. Varun Deliwala has written 8 into 160. What should I do with this? What is 8 into 160? Yes, Varun, you want to say something?
Sir, I was thinking, like, if it requires 1 Gbps, like with a small b and 8 seconds to transfer, then about it would take 64 seconds for 1 Gbps with a capital B to transfer. Similar note.
Okay.
And for 20 would be 20 into 64, and so that would be 8 into 160, like the same value. But yeah, the 20 into 64 would be nearly equal to 1280.
Okay, so see, why I discuss this problem in this manner is, see, most of the problems when you discuss them at at a very fundamental level, what happens is you also create solutions which people have already created, and that is the art of innovation, right? I would this discussion is very important, and you are involving in this. The solution which I just forgot the name, who said that I'll create a iterative copy on the physical server too, and the real solution is quite near to it, right? And the real solution is this. Just a moment. Is it visible?
Yes, sir.
Okay. The real solution lies in this paper, Live Migration of Virtual Machines. They are talking about migrating a virtual machine from one physical server to another physical server without making it down. It can continue to serve requests and still get migrated with non-noticeable downtime, right? Again, it is an academic solution which created a complete technology. Remember, a student whose name is Jacob Gorm Hansen, you can see the name, from TU. You might have heard about UCD, right? University of Copenhagen, Denmark, one of the top-notch, university with the highest paying scholarship, right? And this one is again a collaboration between your Stephen Hand, Jan Pratt, Andrew Warfield. I hope you remember these names who developed the GEN. The same team collaborated with them and created live migration of virtual machines. Right? Now, how do you migrate virtual machines with so minimal time is what they have done. And the solution is little bit different. Let me give a hint, and then we can, in the next session, we can talk about the complete solution. So this is my board. This board is visible. So one of you said I'll make an iterative copy. Let me do something else. Let me create connections to a shared storage server. Is board visible, Kirtan?
No, sir. I think
No.
you'll have to
I'll
share
do-
the screen.
I'll do a new share. Now it is visible.
now.
Yeah.
Yes, sir.
So between these two physical servers, I'm creating another server, and this server will be known as storage server. Storage server. And this storage server is a volume-based server for block device. And what it keeps? It keeps VM disks. Okay. So physical server 1 is running VM1. The disk of VM1 is not here, but here. Okay. So physical server 1 does not have a disk of VM1. Can we run an operating system like this? Yes, why not? What is the problem? Disk is available on this another machine, but operating system is running here. So the data from main memory to disk goes via network to disk and again come through disk to network. This is the purpose of storage area network. You might have heard about these two names, NAS and SAN. Network attached storage and storage area network. If you talk about real production servers or clouds, computational servers and storage servers are different. You might have heard about Amazon EC2. Yes, Amazon EC2 is a computational server. They have S3 storage service, which are storage servers. So where is the disk? Here. Let us say the name of the disk is VM1.vmdk. I'm transferring this VM1 from physical server 1 to physical server 2. I don't need to transfer disk. I just need to pass the reference. Yes, I don't need to transfer any 20 GB data. And it would make sense.
But
This
sir,
simple-
won't this? Yeah.
Yeah,
So won't
please-
this degrade the performance, because every time a request is there, we have to fetch or from the storage server.
Mhm. See, this storage server is very high performance storage server. Okay. Second thing is, let me ask a fundamental question. Which is faster, hard disk or network? Now this question is pretty random, right? We require certain parameters, but in general, what is fast, hard disk or a network?
Network.
Network, okay. So when network is fast, your hard disk is slow. You are talking to your hard disk, you are still talking to your hard disk, but there is a faster mechanism in between. So why would it slow down?
Okay. Yes.
Right? Let me give you an important idea. 1 Gbps is on your laptop, desktop, all these machines. When we talk about servers, we are talking about 100 Gbps. I have servers which supports 100 Gbps. There are servers which support 400 Gbps interconnectivity using fiber, not on copper. Copper we can reach up to 40 Gbps. 100, 200, 300, 400 Gbps. So I'm talking about a channel known as FireWire. FireWire. Please have a look. They support 200 to 300 to 400 Gbps, and all the data centers in cloud use this. So storage is cheap, but it is slow. Network bandwidth is also cheap, but it is very fast. Right? Okay. So any more questions on this architecture? In the next session, I will start with this paper. This paper is also highlighted. This is also pretty simple. Please have a reading. You would realize the importance of innovative solutions, right? So I don't have that video available with me. Otherwise, I had a video of our lab in which I have 2 physical servers in front of me. One physical server and operating system is running a CPU program to show counting 1, 2, 3, 4 printing on the terminal up to, let us say, 1 billion. So, and I, as a magician, I say migrate from here to here. And immediately my student press VM migrate from here to here. And the virtual machine starts running on the second physical server. And whenever we do live workshops, we showed this, and it makes an impact in the mind of the student. कि एक virtual machine, एक पूरा operating system चलते चलते यहाँ से वहाँ चला गया within less than 1 second, right? And it is doable. So this is one initial part. When we'll see the paper of Jacob von Hansen, we will also realize what are the other important things needed for this quick transfer. Right, we'll see in the next lecture. If there are any more questions, we can take. Right.
Yeah, very interesting. So Friday at 1 p.m. is it fine?
Yes, sir. Friday 1 p.m. is fine.
Thank you. So maybe they may not have any question. Would like to.
Yeah.
So I will be conducting my session tomorrow, Kirtan, at 11.
Okay, sir. And I have already shared the papers you went through in
Yeah,
today's
papers I saw
session.
that. Good.
with the
Thanks.
students.
Thanks for that. Thank you, Dr. Gaurav. This is very interesting, and I think this kind of problem which you have posed is very interesting. Let them think also.
Yes. Yeah. Thank you, Professor Chaudhary. Yeah.
I have seen that video, so maybe I have perhaps that video is with me. I will check if I can show
Okay.
them. in
Okay.
class.
Then that would be
We'll
good.
try. Sure.
So I'll
Okay.
take your. Yeah.
Sure.